screen so you can control how you want to advance the slides.
Give me a moment here. All right, do you see the screen now?
No. Oh, yeah, here. Good.
Okay, so I will try to help us with time. Thank you for having me here. I'm Jessie Carman, the Earth System Research and Modeling Division Chief within the Weather Program Office, and very glad to be here, if only virtually. OAR's motivation for these efforts is that we want to facilitate the internal consistency for development to get a living and improving model, and then also to reduce some of the personnel burden, and this is some of what Kevin was referring to. We can't support divergent structures or infrastructures. We also want to leverage some of the EPIC and UFS developments that are ongoing, and this will also give us the ability to utilize forecast tendency and knowledge. At the same time, we have legislative drivers that sometimes appear conflicting or mutually exclusive. But I do note that they tend to have considerable intersection over disasters, planning for disasters, especially at extended ranges. And so we balance our investments. They come from various programs, and I note that S2S efforts may find support in various of these WPO efforts, and that multiple efforts across time scales can lead to SFS improvements. This is one of the benefits of having an internally consistent infrastructure as well. We also balance investments in various non-competitive actions with other agencies, as well as cooperative institutes. Within WPO specifically, the Subseasonal to Seasonal Research Program advances some goals identified by NOAA in the Weather Act to improve the skill as well as enhance the value of S2S products. And the program does this via external awards, internal NWS, and it should say OAR as well, projects, infrastructure support, and interagency coordination. Right now, we have a focus area on Western states hydrology, but this infrastructure ought to give us the ability to change focus area as the nation's needs change. I mentioned UFS. We have our standard view of UFS and its components. What I'm looking forward to in this workshop is more discussion of some of the progress being made in these various components. As we talk about UFS and its specifics, I don't want us to forget about some of this multi-model ensemble infrastructure. We want to work on the SFS model and have it participate in these interagency efforts so that it will be a functioning part of the multi-model ensemble, but also note that we can use these ensembles as proving grounds for the developing SFS or for upgraded SFS versions to see how they are doing. So to pull it all together, our multiple efforts leverage multiple grant programs across time scales, as well as different programs within WPO and efforts elsewhere. And we hope to fill the gaps in the transition pipeline in that way. We are planning a fiscal year 25 notice of funding opportunity, and we're hoping for that information to be available this week. So pulling it all together, we have multiple efforts and hope that we can channel these improvements into the UFS and facilitate the resolution changes the post-processing, the tools that are needed for the users, and I'm looking forward to hearing more about that. And thank you very much. And best of luck for the rest of today with connectivity.
Hey, so the next session is about the S2S modeling and the prediction challenge and opportunities with the 3 keynote speakers. The first one is Dr. Sarah Kapnick, NOAA data scientist. She has a very busy schedule, but she made the time to make this short video recording to be displayed here. This invitation was coordinated by Vasila Sao at the CPC. So we are very grateful she can make this recording. She has been chief scientist at NOAA. Before that, she has extensive experience at the intersection of climate science and economics. Recently, she served as the managing director at JP Morgan in the role of senior climate scientist. Dr. Kapnick was a physical scientist and the deputy division leader at GFDL. Her work spanned seasonal climate prediction, mountain snowpack, extreme storms, and water security. So let's see her presentation.
Hold on.
Okay. Okay.
Cool.
Yeah, that's a very short but very sweet encouragement for all the researchers. Hasten your transition from research to operation. One Steve is working on the slides. The next speakers, Magdalena Balmaseda from ECMWF. She's going to talk about a lot of science, how the research helps the transition at ECMWF. She's the leader at the predictability section in ECMWF. She has been contributed to many fields in this S2S, including the ocean CS component, the coupled real analysis, the understanding of climate signal. Her research covers a wide range of areas, including the forecast design, the predictability, the skill interactions. She has been helping bridge the two communities between the climate and the weather, the observations, modelers, oceanographer, and meteorologists. Let's welcome Magdalena.
Hello, good morning, everybody. Can you hear me? Yeah. Thank you to the organizers for giving me the opportunity to speak. Please let me know when I'm about 5 minutes close to my time, because I can't keep talking for long if I don't have a watch here. And yeah, I'm going to present what we are doing at ECMWF in the area of subseasonal and seasonal forecasts. And maybe just as background, ECMWF, the interest is the medium range. We try to follow a seamless approach, more or less seamless, if only to simplify and to streamline the development. The subseasonal forecast is updated at the same rate as the medium range. It's the same cycle, only at a lower resolution, and it has reforecast. So we have the subseasonal more or less anchored to the medium range forecast with quite fast cycles. Every year is updated. The seasonal forecast, the reforecast are more expensive, and then is updated every 5-6 years. This time is going to be, the next update is going to be in 2025. Last update was in 2017. So it gives you an idea. But the science is basically the same. And I'm going to talk about the science that we do. So what we think is important is to know the system that we have, the strengths and the weakness that helps to communicate the forecast, but also to gain knowledge on what is predictable or what needs improving in the models, because the models are imperfect, everything can be improved. It's good to explore and to play things that we know, things that they can be a little bit math, but it's always good to explore, learn from case studies, advance the diagnostics, advance the metrics, try to get more discerning metrics, new components, and experiment. And finally, these things comes together into the design, the development, implementation of the forecasting system. So there are many things that they can be done, and I cannot talk about all of them. So this talk maybe is a little bit of a potpourri of different topics. I'm going to talk about some errors in the teleconnections, that extratropical teleconnections, errors that we have in the mean state and in the trends. The errors in the trends is becoming an increasingly important topic. And very important also for developing climate models and sensitivities. Some examples of successful forecasts and how we learn by deconstructing successful forecasts. And then I may talk a bit about the role of vegetation, the role of the initial conditions beyond ocean. So far, there has been a lot of attention to the ocean initial conditions, but there are other components such as land hydrology, and also stratosphere that deserve attention. And very little on machine learning. As everybody else, we are engaging with machine learning activities. And then I will summarize what are the upcoming systems. So this is a slide from a paper on, yeah. Should I continue?
Yeah, give me 2 seconds, folks. We just. Steve, can you stop presenting on yours?
Yeah, I can.
Okay, thank you. We're gonna do the entire screen. Here, I'll shift to a tab instead. This is yours?
Yes,
Yeah.
I think so.
All right, very good. Can you do full screen?
Yeah, of course I can.
Okay, so I continue. This is the work by Frederick Vitar. I don't know how to move this. Is there a way of moving this?
No worries, we got it. All right. There we go. That should do it. Okay, that it there.
Yeah.
Okay, great, thanks.
Okay, thank you. So work by Frederick Vitar that showed that even if the MGO skill has been increasing over the years, the teleconnections with mid-latitudes remain challenging. The models, specifically ECMWF model, underestimates these teleconnections. So he has been doing several partial nudging experiments to see if we nudge the tropics, how these teleconnections improve, or if we nudge the exit of the Asian jet. So everything contributes, including the Atlantic itself. Even in the Atlantic, it seems, as you can see in this is an experiment where everything is nudged and the teleconnections are very similar to ERA 5. In these experiments, everything is nudged except the North Atlantic region, and we see that the teleconnections, especially this Greenland law, decreases the amplitude. So because it's going to be difficult to improve the teleconnections especially with Europe, given the variety of factors that influence them. It seems that this is an invitation to explore machine learning results, machine learning techniques. Sorry. So we have started exploring, as you may know that at ECMWF, they have developed AIFS, a machine learning model for weather forecasts. So we are using the same infrastructure and extending it to subseasonal. One of the main challenges is that these machine learning models develop biases. The bias grow very quickly. Even if the forecast skill doesn't, but for subseasonal forecasts, they are not good. So one of the main things is to reduce the bias to begin with and introduce new predictive components like SST, CIs, stratosphere. And that's what we are doing. I mean, this is the bias of the numerical model. This is the bias of the AIFS, the machine learning standalone. And when we introduce SST or CIs is reduced, and when we play with the time step is also decreased. So ongoing, and nothing definitive to conclude. It's just that we are watching. The other, we also pay quite a lot of attention to tropical errors. So one of the errors that has been bothering us is the error in the Eastern Indian Ocean, and that we have a very cold error, very cold bias, very dry bias. And also it is associated with large amplitude errors in seasonal forecast, large spread, especially for the cold events, not for the warm events. It's a very flow-dependent error. So we have been trying to study it. It's very seasonally dependent, as you can see here. So we have used multivariate SST versus zonal mean state, and then you can see the seasonal cycle that it is very pronounced, and especially forecast initialized in May, and they have a very strong errors in the summer and autumn seasons. And as I said, it's associated with large false alarms, if you want, large errors. It's in most of the models, we have these errors, especially those that they have very fine vertical resolution in the ocean. So that we try to investigate what is the relationship, what is the influence of the ocean and the atmosphere. So there is an error that it has two regimes. Is in the warm regime or in convective regime, the errors manifest in the sense that the SST can become quite warm because the convection doesn't seem to be triggered, so the winds do not respond to warm SSTs. As you can see here, this would be ERA 5, and this is the model. And then we have a cold error that is characterized by shallow thermocline, and it happens when you have, yes, this cold tongue error, shallow thermocline, strong winds, very cold SSTs. And this is the one that is sensitive to the ocean and the ocean initial conditions. This other doesn't, the warm regime is not sensitive to the ocean initial conditions. What else? I mean, it has been said already that this forecast, subseasonal, seasonal, but I would say even medium range, the climate change and global warming is a source of predictability. So before they were conceived only as an initial value problem, is no longer the case. Because for two reasons, is that the climate is not a good predictor. So climatology is less informative. But also we can, with observations, we can represent the time variations of the greenhouse gases, the aerosols, etc., and that signal goes into the, manifests into the forecasts. So from that point of view, we are bridging the gap between medium, seasonal and decadal, because it's the same problem. Therefore, trying to find out how these errors, these models predict the trends, the observed trends that we see during the reforecast period becomes very important. And I'm going to talk about two areas that we have studied, is the Arctic and the Arctic amplification. We see that the forecast, even at subseasonal time scales, have errors capturing the trends in the Arctic and also in the tropics. The problem that we see with ENSO, the false alarm on warming. I think I may be going too fast or too slow. I don't know. It's a lot to cover. Just to say that there are in the Arctic there are two regions that they have different sources of errors, but in both cases there are two time scales. One that manifests very quickly in the first week of the forecast, and the other that lasts longer. The one that manifests in the first week into the forecast is usually related with the initial conditions of the ocean or of the sea ice in this case. In this case, it has to do very much with the way in which we couple the sea ice to the atmosphere. It has to do whether how much of the sea ice thickness and the snow thickness the atmosphere sees. If by having a more physical coupling, this error can be reduced quite quickly. And this is a development that is going to be implemented now in ERA 6 in the next reanalysis, and also in the forecasting systems, medium range to seasonal. It is obvious, so it's not rocket science, but it's good to see that it has an impact. The other error has to do with the tendency of the models to warm the equatorial Pacific and to produce more ENSO signals. In ERA 5, there is not trend over this region. In system 5, that is our seasonal forecasting system, we have a warming. This manifests on the SST, but also in the ocean heat content. and it also manifests on the winds. What is surprising, while ERA 5 doesn't have trend on the SST, what it has is quite a strong easterly trend in the winds, and it has also a southerly trend on the meridional winds, a trend that is not present in the forecast. So we have submitted just a paper trying to analyze the reasons for this. It's not going to be easy to solve, but it's good to understand. And it's good to understand because it may affect actual forecasts, like the forecast and the models. Most of the models have problems sustaining the triple dip La Nina, so they wanted to get out of this triple dip La Nina quite quickly in such a way that when the El Nino happened in 2023, we didn't know whether it was a false alarm or it was going to be real. So it is quite important to have a bit of a grasp of what is going on. And what we show is that these are the forecast errors of this during this triple dip La Nina. Forecast initialized in May, verifying in November, and these are the trend errors. If we look at sea surface temperature winds, they have the same footprint, so they are related. The other activities try to learn from successes. So it's not common that we have good predictions of the NAO at seasonal time scales. We had one in December, DJF 2019, 2020. Most of the models predicted NAO positive, the seasonal multi-model. So we try to say why there is so much convergence, and also it verified. So what we did was not only that case, but also two other cases. It had to do with the Indian Ocean being quite warm. So we picked another two cases where the Indian Ocean was quite warm, 1997-98 and 2015-16. These two cases were El Nino years. So we deconstructed the forecast by suppressing the SST anomalies in the Indian Ocean or in the Pacific. So what the results showed, these were done in uncoupled mode. Here is the reference experiments by putting climatology in the Indian Ocean, we favor NAO negative. So warm anomalies in the Indian Ocean favor NAO positive. Equally, the Pacific, the ENSO anomalies favor NAO negative. That was quite clear. And this was particularly the case in 2015 and 16, where the competing effect between the Indian and the Pacific Ocean, that's a reason for the uncertainty, but in 2015 and 16, the Indian Ocean anomalies were stronger, influenced the NAO more strongly than ENSO, as you can see here. Why was that the case? And it seems that it's related to the polar vortex. So this is the impact, stratospheric polar vortex. This is the impact of removing the Indian Ocean initial conditions in the stratospheric polar vortex. This is depth and this is time. No, sorry, height, and this is time. And this is the impact of removing the warm Pacific. So, we went a little bit further to try to simplify the problem into two variables, that it was the NAO index versus the stratospheric polar vortex. We did large ensembles, 100 ensemble members, and with that you can represent what is the phase space. This was the ensemble mean and this is the observations. And with this you can calculate conditional probabilities. You can also see what is the impact of removing the Indian Ocean. Warm anomalies in all the cases was to weaken the polar vortex and to produce a NAO negative. But it also changes the conditional probability of the NAO in condition to the polar vortex. So it's a bit nonlinear. And it seems what the results for this year, 2015-16, stand up very anomalous year due to the stratosphere. We don't know exactly why. I don't know whether it was also the year with the QBO. I don't know whether you remember change sign in the middle. Something to be continued, but it's interesting. We have been playing, also investigating what is the role of vegetation, both prognostic but also prescribed. We have quite a lot of data sets now that we don't use in the reforecasts. So what would happen if we could have time-varying vegetation in the reforecasts? The results show that actually the atmosphere-land feedbacks mediated by vegetation, they are quite diverse in different models. They influence the trends and they influence the extremes. There is not agreement on how they influence the trends, but there was agreement on the impact on the heat waves. When you have a heat wave, an extreme heat, the amplitude would be higher if you have a prognostic, if you have a time-varying vegetation. The vegetation decreases, as you can see here. This was done in 3 models, and in the 3 models, it showed similar effects. However, we are not going to implement this time-varying vegetation in our next seasonal forecasting system. It's still immature, both the initialization and also the modeling. So it's something that it will be probably in the next, in System 7 or in ERA 7, but not in ERA 6, not in System 6. More work is needed. We are continuing exploring and paying attention on how the seasonal multimodal represents the land atmosphere feedbacks, specifically the soil moisture and evapotranspiration. And this is this sensitivity defined in this manner in ERA 5, and this is the bias in the multimodal. They have a bias, very strong bias in this region and in this region. The bias is towards the models. They are more soil moisture control rather than energy control, I believe, according to this diagram, that if there is a slope in this variable as a function of soil moisture, that means that the controlling effect of the evapotranspiration is the soil moisture. If it were energy, it should be flatter. So the models rely quite a lot on this soil moisture evapotranspiration feedback that probably is too strong. That's for the science. Coming back to the implementation, something that we need to think, well, is the initial value problem. I said before, beyond the ocean and the stratosphere land. And one of the things is the consistency between the reforecast and the real time. So this forecast needs reforecast. If we don't have consistency between whatever initial conditions have been used for the reforecast and the real time, we may have quite a lot of jumps. And this is the case at ECMWF. The land data simulation has changed. They have included a multi-layer snow model in such a way that now the initialization from ERA 5 is not good for the reforecast. It creates inconsistencies. This is a measure of the inconsistency between ERA 5 initial conditions and the new operation. So this means that the new subseasonal forecast that is going to be implemented in November will require its own land reanalysis to be consistent with the real time. I take the chance to say ocean initial conditions, of course, matters. There is going to be a very nice opportunity, and I think Yosuke Fuji may present that within the SYNOPS program on OSIS for S2S, Ocean Observing System Experiment for S2S. The results show that many of the bias that we see, and the ocean observations and the initialization impacts both the mean state and the trends of a forecasting system. Beyond the scale is difficult to measure, but trends and mean state is they are easy to measure. And I think this has to be taken into account when developing a coupled model to make sure that some of them, what we are correcting, we are not falsely correcting for errors in the initial conditions, but we are correcting for errors in the model. So it is important, the ocean initial conditions affect, of course, the Viernes feedback in the Pacific, the Indian Ocean, the tropics are very clear, but also the extratropical atmosphere, as it can be seen there. I'm going very quick, but if you want more questions, I will be here during the rest of the week. And the ocean, I mean, now we are in the process of producing a new ocean reanalysis, ORA-6, how Suo will talk about it tomorrow. This has quite a large impact on subseasonal and seasonal forecast, especially on ocean variables. It has better position of the Gulf Stream. It has colder ACC. And this impact on SST continues with lead time into the seasonal forecast. So it's quite a large impact. And it also affects the precipitation and the storm tracks, as you can see there. It's under development and under evaluation. There is increasing interest on bridging this gap between seasonal and decadal. So the 2-year forecast horizon is receiving increasing attention. This is an example of what happened in 2023 and for El Niño 2023. The forecast, 2-year forecast, initialized in February 22, that it would be this one, was very similar to the 2-year forecast initialized in February 23. To the 1-year forecast. So there is a scope for this, there is a skill, and users like seamless information. So a way of providing a continuous information between seasonal and indicator could be quite interesting for users. I think I may need to go further. There are other activities like ocean resolution, atmospheric resolution, stochastic physics for sea ice, time varying aerosols, but I leave it for the time being. Quite important is any development to evaluate timing, evaluate, and have metrics. Something that we are increasingly interested is in metrics not only for extreme events for users, but also because these metrics for extremes, if we aggregate temporal statistics on daily rather than seasonal average, the statistics can be more significant and more discerning. So you don't need so many ensemble members to distinguish whether a system is better or not. So instead of is temporal pooling instead of temporal averaging. So with that, I go to the next system, forecasting system. So there was some research. Frederick Vittard showed that there was more value in increasing the number of ensemble members, the frequency of the forecast, and the frequency of the reforecast than increasing the atmospheric resolution. So for the same computer and the cost envelope, he proposed to go to have extended subseasonal forecast issued every day, 100 ensemble members. So that started last year, I think. So now we have that, and then the reforecasts are going to be produced in the same period every 2 days, 10 ensemble members. And that upgrade on the reforecast is going to be implemented in November this year. For the seasonal, we go from system 5 to system 6 in 2016. We keep the same resolution, only changing the vertical resolution to 137 levels. We are going to do the plan for twice a month, 100 members, up to 7 months. Then every month after up to 1 year, and twice a year up to 2 years. That's for the real-time forecast. And then for the reforecast, we will have a main set from 1993 to 2024, and similar to what we have now. And then an extension, a back extension, trying to cover the 60s. And that's it. That's the end of my presentation. Just to say that the forecast and these time scales are increasingly relevant for a changing climate, and research is needed for a continuous evolution and uptake. Need to engage with the wider observational and data simulation community, because these forecasts are an initial value problem, but we also need to engage with the climate community because they are a force problem. Some of the long-standing issues are going to be very difficult to solve, so we can not wait for these problems to be solved. We have to implement and be aware and communicate and calibrate a posteriori. And I think that's basically it. Thank you for your attention.
Yeah, we don't have time for question and answer. Maybe we can wait until other session. Let's go to the next speakers by Bill Merryfield. Thanks, Magdalena. The slides are going to be available on the web page.
Oh, God.
So next speaker is Bill Merryfield from ECCC. He's a research lead at the Canada Centre for Climate Modeling and Analysis in Victoria, British Columbia. For many years, more than 10 years, he has been leading the efforts in applying the CCCMA's climate and earth system model in predicting the seasonal and decadal time scale. His efforts has contributed to the both operational seasonal forecast as well as the multimodal decadal forecast. He's currently serving as the WCRP working group on subseasonal to interdecadal prediction. Welcome, Bill, to give the talk on the perspective at the ECC.
It's not shared. Okay.
Here.
That's right. Yeah. Great. Yeah, so in late 2011, a system based on 2 versions of CCCMA's coupled climate model was introduced. This was the first version of the Canadian Seasonal to Interannual Prediction System, or CANSIPS. So with the coupled system, the range was extended to 12 months. And since there have been several newer generations of CANSIPS based on combination of CCCMA's climate models and a couple of models derived from NWP.
Bill, I
system.
apologize. We're having an audio issue.
Okay.
I gotta interject. I apologize, everyone. Can you hear us all? Thank you very much.
Entire screen.
Okay. My apologies, Bill. Please continue.
Yeah, so the most recent version, CANSIPS v3, was implemented just this past July. I'll be describing that later on. Right, so naturally this approach of combining models, climate and NWP models, requires a lot of collaboration within the department. That looks like this. CCCMA, the climate model developers, interact with the NWP developers at RPN, and both interact with the operational side at MSC. One aspect of this is a push to develop new sector-relevant products, and a new aspect of this is the involvement of the Canadian Centre for Climate Services, that circle, that oval near the bottom, and who will be providing an advanced platform for dissemination and also channels for end user inputs. Right, so why go to the trouble of running multiple models at a single center and all of the challenges and complexities that that brings? Well, this plot is from a 2008 paper by Slava Karin, which was itself based on a old 2-tier atmosphere-only system with 4 models having 10 ensemble members each. And so the different curves, the bottom one represents the skill, in this case, 2-meter temperature skill averaged over land at 0 lead, that you get from one model with different numbers of ensemble members. That's the circles, and then squares are all available combinations of 2 models, and so forth for 3 and all 4 models. So we see, first of all, that there's a big jump from 1 to 2 models, and then tends to be a bit of diminishing returns. So for the recently retired CANSIPS v2.1 system, so the dark blue arrow indicates the performance gain going from 1 model with 10 ensemble members to 2 models, combining 2 models with 10 ensemble members for a total of 20. And the light blue lines indicate, so the dots at the end of each curve are an extrapolation to higher numbers of ensemble members. And so the short light blue curve indicates that only a fraction of this performance gain is due to the increase in ensemble size. If we had just taken 1 model and doubled its ensemble size, by far the largest performance increase is due to the model diversity. So for the new CANSIPS v3 system, so the ensemble size has been doubled by combining the ensemble that had been run at the end of the last day of each month with a backup forecast that had been run 4 days earlier. So in this way, we double the ensemble size with no cost, at least in real time. That backup forecast has never actually been needed. And we see a similar picture where now the upper 2 dashed blue lines indicate the performance gain relative to the previous system with 10 ensemble members each. But again, by far the larger part of the increase in performance from the single model is due to the model diversity. So one can sort of look at the value of taking many models with ensemble sizes combined, potentially running into the hundreds. This is the approach used by NMME, WMO Copernicus, APCC, and because of the sort of overwhelming number of models and ensemble members, this gives a performance increase that it really exceeds what any one center can likely provide. So how well does this approach work relatively in practice? So this shows skill average globally for 2-meter temperature anomaly correlation, all initial months for the approximately 15 WMO global producing centers. And so we see that the Montreal ECCC forecasts perform relatively well despite the use of comparatively inexpensive models and modest ensemble sizes. So the performance of the V2.1 system was exceeded only by ECMWF in the UK Met Office, and with, as we'll see with CANSIPS V3, this will improve further. In fact, we've already started to see that in July and August initial months. And again, by combining all of these models, despite their uneven individual performance, skill unequaled by any of the individual systems is achieved with a multi-model ensemble, the grand ensemble from all centers. So one thing we've learned is that what makes a model good is sometimes in the eye of the beholder. So taking Nino 3.4 skill in the initial CANSIPS version as an example, the left shows an analysis of the NMME models. This is Nino 3.4 anomaly correlation in winter as a function of lead time. And it shows that CANCM4 was pretty clearly the most skillful model by that metric. On the right, looking through a different lens, this is the random walk approach of Del Sol and Tippett, where it's an RMSE-based metric where each forecast from each model is compared to CFS V2. And so the lower curves are actually the more skillful ones. And by this metric, CANCM3 was actually the most skillful, whereas CANCM4 was back in the pack. So that's sometimes something to keep in mind. So turning now to CANSIPS V3. The previous CANCM4I model has been replaced by CAN-ESM5. This is the first Earth system model that's been introduced in CANSIPS with an interactive carbon cycle, terrestrial and ocean ecosystem components. And the other changes are listed here. One thing to note is the atmospheric and land resolution is not changed. It's still at T63 or 2.8 degrees, which is extraordinarily coarse by current standards. And also the NEMO ocean model at a nominal 1 degree resolution has been introduced. So the initialization approach is similar to previous CCCMA models. So we take 6-hourly reanalysis, nudge the atmospheric variables. So we're now nudging ocean temperature and salinity as well. And as before, SST and sea ice nudging. And each ensemble member, this is done in a separate coupled assimilating run, different one for each ensemble member, because of the moderation of the nudging coefficients that develops an ensemble spread that provides perturbed initial conditions. And then we simply apply these as initial conditions for the forecast without nudging. The data sources are here, essentially the ECMWF reanalyses, ERA5 and ORA-S5 in the hindcast. And in the forecast, we use, since ECCC does not have its own reanalysis, we use its NWP analyses, which are available in real time. Right, so CAN-ESM5 has been around for a while. In fact, it was CCCMA's CMIP6 model, but we didn't rush it into operations. So the main reason is that the simulations, CMIP type simulations from CANI-SM5 really did not simulate ENSO very well. So the upper panels show a standard deviation of NINO 3.4 as a function of calendar month. So we see that CAN-CM4, actually here its close cousin CANI-SM2, simulated ENSO amplitude quite realistically, a little bit slightly too energetic, but with a realistic seasonality. But CANI-SM5, ENSO amplitude is too weak and does not show the type of seasonality that's observed. And we also see kind of similar issues in the composites in the lower row. So finally, the approach we took was to apply a method described in a paper by Karin and Sunoka in 2012, and that's to take the nudging terms and save those, and from those formulate a seasonally varying tendency correction. So we turn off the nudging, but we insert this non-interactive correction. And this is done both for the atmosphere and the ocean. First time I believe that both components have been applied. I think NASA has done this for the atmosphere and GFDL Spear for the ocean, but never both together that I'm aware of. So we tried this both with the nudging settings in the default assimilation runs, and also sort of fiddling the nudging settings to try to optimize the bias correction. So here's some comparisons for 500 hectopascal height biases and near surface zonal wind biases in short runs without bias correction at the top, the default settings at the bottom, and the optimized in the middle, the optimized settings at the bottom. The numbers at upper right are the RMS errors. So we see with the default correction, there's some improvement. We actually introduce some biases, particularly in the Southern Ocean. There's a dipolar bias in surface winds. And here clearly the optimized bias correction does best. Similar for SST and sea surface salinity. Without bias correction, there's some pretty horrendous biases that we see in CANI-SM5 runs in the Northwest Atlantic. The equatorial Pacific SST annual cycle is very unrealistic. This has been connected across models with unrealistic ENSO seasonality, compared to the observed cycle, which has only a semi-annual component. So with default bias correction, the equatorial Pacific SST annual cycle is much improved, and there's some improvement in SST and SSS, but some new biases are introduced, but clearly the optimized bias correction is the best here. So we had high hopes that this would improve the prediction of ENSO, but in fact it did not. In fact, comparing with no bias correction, optimal bias correction as a function of lead time, NINO 3.4 scale was actually slightly degraded with the bias correction. However, for all the other variables, so taking a global view here, SST, 2-meter temperature, and precipitation, the skill was appreciably improved across the entire range of lead times. So at this point, we were satisfied, okay, we can't predict ENSO as well as before, at least NINO 3.4, but the overall improvement justifies implementing it. So why is this? We found, okay, that the bias correction reduces the unrealistic westward extension of the El Nino La Nina SST anomalies that many models show. So with no bias correction, we see the anomalies, these are SST standard deviations extending unrealistically to Indonesia. But with bias correction, the pattern is much more like observed, even if the ENSO is still too weak. And we find in this region where the correction was had this effect that skills for SST and precipitation went from negative to substantially positive. In addition, this appears to have had some influence on teleconnections. For example, Southeast China, that panel in the lower right shows an appreciable positive correlation with NINO 3.4 in observations. And in that location as well, we went from strongly negative to strongly positive skill. So turning to the other CANSIPS v3 model, GEM 5.2 NEMO, This is more of an incremental update, some physics updates to the atmospheric GEM component. The sea ice component has been updated from size 4 to size 6. One aspect is that the non-orographic gravity wave parameterization was retuned. So the previous GEM 5 NEMO, this is showing equatorial zonal winds at the equator. GEM 5 NEMO did not show really any sort of QBO, whereas GEM 5.2 NEMO with this retuning shows a QBO with realistic amplitude and period, except in the lower stratosphere, which is often a challenge. Also, both GEM 5.2 NEMO and its predecessor predict MJO relatively well for a seasonal model, with the RMM anomaly correlation remaining above a half out to almost 30 days. In fact, this is better than the higher resolution monthly forecast using also a higher resolution couple model. So the initialization of forcing data, similarly ERA, ECMWF analyses in hindcasts, the available NWP products in real time. So evaluating CANSIPS v3 versus the preceding version 2.1. So this is now with 20 ensemble members from each model to sort of highlight the improvement from the model development. So v2.1 is blue, v3 is orange, and the two individual models are on left and center, combined system on the right. So for temperature and precipitation over global lands. So we see pretty decent improvement across the board. Similar for 500 hectopascal height SST. There's improvement, again, despite the degradation of Nino 3.4 skill in CAN ESM. But overall, there's, due to the two model combination, there's a smaller degradation in Nino 3.4 skill. So just to summarize some challenges. So because both the climate and NWP sides are using models of opportunity, have very little sort of influence over what those models look like. For example, on the climate side, we've been sort of stuck with this 2.8 degree resolution for some time, even though the model itself performs decently. That's very coarse compared to current standards. Also, since 2019, there's been a fixed 30-month development cycle, which really governs the, so we're almost in a continual cycle now of development and implementation without a lot of time to experiment. So we've been adapting to that. Also, because ECCC does not have its own reanalysis, consistency between hindcast and forecast initialization needs special care. And also, all this collaborative multi-model approach has historically worked well. It really depends on individuals on both the climate and NWP sides, and going forward as personnel evolve, might be challenging to sustain. So in terms of lessons learned, so one is that consistency between the hindcast and forecast initialization and also the processing is extraordinarily important, particularly for a center that, like ours, that doesn't have its own reanalysis. So here's an example from the original version of CANSIPS. So it shows globally average soil moisture in the two models over the hindcast period, which was based on ERA 40 and ERA interim at the time. And then but when we went to real time, the real-time NWP analysis in some sense must have been drier than the hindcasts, and the soil moisture immediately started taking a dive. So through monitoring, we detected this, and the solution was to develop a tendency correction, somewhat like the one shown earlier, that pushed soil moisture climatology back up to the hindcast level. In terms of processing, when CANSIPS v2 was first implemented, there was a slight delay that resulted in key personnel being on leave during the final push for implementation. So the people who filled in did their best, but there did end up being an inconsistency in the interpolation to the NMME grid between the hindcast and the forecast. So some of us will remember this rather interesting precipitation forecast map that appeared on the NMME site. So this was quickly fixed, and to prevent a recurrence, some thorough documentation was developed of all the steps involved in producing CANSEP's forecasts and associated products. So another lesson learned is, as the song goes, you can't always get what you want, but if you try, you can get what you need. And in this case, I think this applies to CAN-ESM-5. We really wanted to have ENSO skill that was similar to or exceeding that of CAN-CM4I. We tried as hard as we could. We just could not realize that. However, through these efforts to develop and implement the atmosphere and ocean tendency adjustments and resulting bias correction, the skill for other important fields such as SST, commuter temperature, and precipitation over land was in fact considerably increased. According to the development cycle, there will be a new CANSEPS v4 introduced at the end of 2026. So it's very early days, but at present, what this is looking like is that combination of CAN-ESM-6, which will be CCCMA's CMIP7 model. Finally, the spectral dynamical core that's being stuck at T63 resolution will be superseded by the GEM dynamical core at closer to 1 degree resolution. Still pretty coarse by current standards, but a major increase for this model. With CCCMA physics and tentatively going to a 1/4 degree NEMO ocean, improved initialization and bias correction through experimentation that we're just getting started with. There will also be a new GEM NEMO version, tentatively with a 35 kilometer using GEM dynamical core NWP physics, and also a 1/4 degree ocean. So we're hoping to have ERA6 and AURA-S6 ready in time to initialize the hindcast and realize those improvements that Magdalena was showing us. So to summarize, the multi-model approach has enabled seasonal forecast performance to be competitive with single model systems having higher resolution and larger ensembles. The development and maintenance of the multi-model system requires extensive interdepartmental coordination. So the skill improvements in CANSEPS v3 came partly from the CAN-ESM-5 tendency adjustments, which improved the ENSO SST anomaly pattern, although the CAN-ESM-5 NINO 3.4 skill remained mediocre. So just to highlight the overall skill improvement versus version 2.1, which is the blue to version 3 and the orange for temperature and precipitation over land. And now this is going from to the larger ensemble and the model development. So, and by sort of crunching the numbers, we found that about 40% of this improvement is attributable, this is across all lead times and initial months, to increased ensemble size, and the other 60% to model improvements. So I'll stop there. Thanks for your attention.
Thank you. Thank you a lot for these two outstanding keynote speaks. I still want to entertain some questions for 5 minutes since we are delayed. Let's have an open floor for 5 minutes question to Magdalena and Bill. If you have any question, please go to the microphone. We can postpone the next session for 10 minutes. I think it's good to lots of material here they present. Any questions? Just raise your hands. Yeah, go ahead.
My question is for you, Bill.
Yes.
Okay. So I'm thinking about your degradation and so skill, and I think in some of the plots you showed, you had in the Karen, in the version 4 of your model, did you have a fresh bias over the whirlpool region? I believe is what I say, and with your bias adjustment, that was mitigated. So it was previously a fresh bias. Did I see that correctly?
The fresh bias was in CAN-ESM 5 without bias adjustment, but I know previous versions have had excessive precipitation over the worm pool. They probably had that bias as well.
Okay, so it just makes me wonder if perhaps associated with that fresh bias of the whirlpool, if you perhaps had a barrier layer bias also. Did you have perhaps too frequent or too strong barrier layers there? And through bias correction, if perhaps that has been reduced, that could play into some of this bias with the ENSO cycle.
Yeah, quite honestly, the barrier layer is something we've not really looked at. So I know a number of models, well, particularly CMEP type models do tend to show this excessive western extension, not so much, I think, in more recent higher resolution models. So yeah, I'm not sure exactly what is the physics. I sometimes suspected that it might have to do with resolution, topographic barriers, etc. But yeah, we have not looked at the salinity aspect.
Any other questions? Magdalena is there. Any questions for her as well? Okay.
I guess this is really a question for both of the last speakers. In seeing the talks, you guys are running different models, different resolutions, and Bill, I think you actually explicitly said this, that you're like the MJO prediction is actually better in your coarser resolution model. So I think my question is, is the scientific community with operational centers included, are we really thinking about seasonal prediction and how to best use our resources correctly? I mean, there's always the temptation to drive to higher resolution, but I see over and over again that it doesn't necessarily make things better. So it's just, that's my question. Do we need to rethink where we're spending our resources? And Magdalena, you just talked about work that Frederick had done in figuring out how to use that. So I guess it's really for both of you.
Okay, well, Magdalena's coming up. I'll answer first. So I agree, resolution isn't everything, but I think it does help in certain cases. Like recently, experiments of NCAR have shown that high resolution, very high resolution decadal predictions by current standards show very interesting and pronounced skill improvements in regions such as the Southern Ocean, etc. So I think, yeah, you can do reasonably well without going to very high resolution, but and even, in some cases, it may even sort of introduce noise in the fields that if which is realistic, but might, if just taken at face value, affect the skill. But I'm happy to hear Magdalena's perspective.
Yeah, I don't know. That's the answer. Whether we are thinking carefully about the sources we expect to demonstrate. I think you have to distinguish between horizontal resolution in the atmosphere, vertical resolution in the atmosphere. So our experience at the subseasonal and seasonal forecast is there is difference in the scale between, say, 60 kilometers and 30 kilometers, but if you go farther, you don't see much at this time scale. You can see it in the horizontal resolution. In the vertical resolution, it has to be commensurate with the vertical and horizontal resolution, especially in the tropopause, has to be commensurate to solve some vertical waves. So, in the ocean, the quarter of the degree seems to be over the 1 degree. In the tropics of the quarter. So I think that's relatively the vertical resolution also matters. Should we go beyond quarter of the degree, it would be terribly expensive. Other ways, more clever ways of representing resolution with machine learning or with the measures with the stochastic parameterization. That's my answer. The question is that.
I have a more simpler question. I have a more simpler question for Magdalena. What is the timeline on P6?
I realized that I haven't talked much about the components and the timelines. ECCC is going to start production next year. And it will be finalized probably by the 6. I don't know when it's going to catch up with real time. For 2027, the idea is going back to 1950s as well. So I don't know when it's going to be completed. It's going to be initialized with OS6, the SSDs, and provided by OS6. So at the moment we are doing a lot of experiments which how to produce good SSD records. So the critical question for Bill, I guess, if you are going to use OS6 for the operational system is when ECCC is going to catch up with that and be able to stay with that. That's
Sure. This is for both and Magdalena. I was just, you made a nice comment on how like multi-model ensembles, when we're pulling multiple models together, we tend to increase the skill a bit better. And then you can kind of saturate how much skill added value just increasing the number of members. And I was just wondering, like, is there a coordination effort across the centers to keep your model structures distinct, to keep increasing the skill when you're kind of pooling these different guesses, I guess, about like how the Earth system works, and what are your thoughts about, you know, the different ocean models that are going into the different centers?
Yeah, it's a really good question. I think actually both in the prediction and climate simulation, things have been tending in the opposite direction, where there's, you know, different centers are picking up other people's components and putting them together. And I mean, in terms of not having control over model development, that's one thing that's affected us is we basically had to import NEMO, which the NWP models also use. Personally, I'm Team Mom. I would have much preferred to bring in Mom, but we did not have that choice. So yeah, so going forward to concepts before the model diversity, you know, since we're in common dynamical core, will mostly be due to different physics packages and land models. So.
All right, we had some question times. So right now we are 10:24. Let's have a short 35. Okay.
Yeah, we'll give them an extra minute. We'll be back at 10:35, like you answered about.
Okay, 10:35. Short break. Let me start next session.
Then I would cut our people's lunch time.